Okay, as Monsieur Messier, Alewan CEO, this morning mentioned, robotics will create a lot of jobs, millions, he said. So we need people who can apply for those jobs. So we need millions of engineers. That's why my speech is about how we can interest young people in STEM topics, and especially for engineering. So, the content of the speech is, first of all, I will tell you something about my institute, where I come from, where I work. Then, the education labs, something new at the Aachen University. We have several different labs for several research topics. And after that, I will introduce you our methodological and didactical methods when how we build up our robotic courses. And after that, why we really use now in this context. So this is the place I work actually. It consists of 3 institutes, and the special thing about this is that we have on the one hand, we have the engineers, the IMA, they're for computer science and mechanical engineering. And at the same time, we have the Center for Learning and Knowledge Management. So there are mostly human scientists, and we have a lot of projects on which both institutes are working on. So we try to make all projects in the interdisciplinary way. And the third pillar of our institute is the IFU. I work there, and we're an associated institute and for management cybernetics. I think 2 years ago we got a new head of the institute, Professor Jeschke, and she said that cybernetics is it comes from the technological view, and we used to do only management, so economical aspects. So now we are also on the technical part. So here you see we have the economic and social cybernetics and the engineering cybernetics, which take care of the labs for the children. So when Professor Jeschke started 2 years ago, she had a big vision. She wanted to introduce the RWTH Aachen University Education Labs. What does it mean? She wanted to connect different engineering disciplines under one roof, so they should work together and collaborate. She wanted to offer space for creative and individual work for the children, and that they can experience current and future technology, what they don't have the chance of usually at school. And the long-term goal is to give those children an orientation for their career, especially for the participating disciplines, so engineering and that stuff. And that's the education labs right now. We have on the first one was the Roscoe, especially for children. I'll tell you something later on. The InfoSphere, this is for computer science, and the DLR school lab, which is fairly new. It will start next month. And she still plans to add more labs, so more disciplines come together in one place. So the Roscoe, it's funded by the Ministry of Innovation, Science, Research and Technology of the state in North Rhine-Westphalia. So it's not the Germany itself, so it's only the state. But their pupils have the possibility to design, construct and program their own robots, especially because we use legal mindstorms for that. And this is the focus on primary school and first grades of secondary school. The other lab, the InfoSphere, it's the same funding, and they really look at the fundamentals of computer science. So they're dealing with the basic topics and try to make concepts, methods and tools of the computer science available and visual, touchable for those children. but they focus on, like, they have pupils, teenagers, students, they offer courses for everyone. And then we have the DLR School Lab. I don't know if you know the DLR, the German Aerospace Center. It's very famous. And yeah, this lab, especially for career orientation, and it's for yeah, students of secondary school, so the teenagers who might go to university one year. Yeah, the DLR has core topics. It's aerospace, energy, traffic, and safety. And we want to address the automation and the robotics in these core topics. And especially they want to take gender and diversity aspects into consideration, so we really want to attract girls and women to choose engineering as a subject of study. So now the big question is, how do we teach pupils those complex topics? Robotics, sensors, cybernetics. And there was a very smart man a long time ago, Confucius. He said, tell me and I will forget, show me and I may remember, involve me and I will understand. And that's the idea of our dual cycle of learning, which I present in the following slides. It's a didactic design based on a dual cycle of work-integrated learning. So we developed that in the work life, but we adapted it and put it to the labs. And yeah, it's an iterative loop of experience. We have it here: experience, reflection, and application of the gained knowledge again. So first, this is for the demonstration of the roboscope. Children come into the lab, and there we have a lot of toys. These little robots, not very complex, only with a remote you can control them. And they're not that fancy. Then now they walk usually like this, and yeah. They're just for initiation and confrontation and motivation. So children, they are not afraid of the topic. They touch it, they play with it, and they really have fun together with their colleagues. Yeah, we want to give them an easy access to the topic of robotics and reduce the inhibitions they might have of the topic. Because then we have the reflection part. And this is, yeah, we have here the room where they sit. It's classical, but so the teachers in front, they address the things the children observed before and give them some background knowledge about the specific things. And yeah, so, and this are usually micro-training models, micro-teaching modules. About 30 minutes long. They have 2 of them in one day, and there they get all the knowledge they need to program the mindstorms and to build them. And yeah, we make this because for the rapid exchange of knowledge and yeah, to get the initial, to fill the gap between the initial experience and the later work the children have to do. Yeah, it's a second step, so this is not really a step, this is the mental model. Children usually get then, after that they get the boxes with the Lego and start to build their own robots and with the sensors and everything. They had a first practical experience, giving them the chance to really use the knowledge they gained before. It's more sustainable, so they will remember and can adopt the knowledge to another task. So then they build their robot, and then they have another experience, the tournament area. You can see right here, so 3 boxes, and they have to build a robot to follow a path. And yeah, they can test their program models and connecting again the practice with the theory, because then they notice, okay, the others, they are better, they are faster with the line, and they try to improve themselves on their own. Then we have another reflection module, the micro-teaching, and then we if the children have more questions about the algorithms and how they may improve their vehicle, we give them some background knowledge about it, and then they really can deepen their knowledge and improve their robots. Yeah. After that, hopefully they have a generalized model. So we only start the learning cycle. They get a picture of the field of robotics, and usually we have school classes, and the teachers they take this experience and bring it to the lessons later on and use it, so they get more into math and that stuff. So, and what's the other things they learn with it? Problem-solving strategies, because they get a task and they have to solve it by themselves. Only later on they get help by the teachers. They have social skills. They gain it because they have to work in groups. At least 3 people work together. They have to be creative. They can build up the legal models, and also they have a tight schedule, so they have to learn time management later on in the work life. It's a crucial thing you have to have good time management. I hope my time management is not too bad. Okay. And sense of responsibility, because they work in a group and there's no one, like there are only 3 people, and they really need those 3 guys or girls to solve the task. Yeah, and the other stuff, interest, engineering, and science topics. So I said we also have the DLR lab, and this is kind of the core topics of the DLR, the aerospace, energy, traffic safety, and robotics. And we try to bring those core areas into the application areas. So it's construction technology, information technology, electrical engineering, and cybernetics. Here we have something, they have to program a drone which should follow a little car on the ground. And here the discussion about the flight dynamics of a quadrocopter. So if one engine fails, what does the other engines have to do? And then we have the energy. That's about they have to analyze how the wind is coming to the wind generator, and then how the wind generator adjusts to the wind, so it gains the most energy. And traffic and safety, it's more navigation along a path, but with more than one vehicle. So if one stops, the other should stop, and it's a little bit with the recognition and stuff. And then we have the robotics, which I'm going to talk about right now. So we want them to program now that he performs the going. Also, like as I said before, we want to address the application areas with now. Now is perfect for that because there's nearly everything in it. For example, construction technology, we might make an experiment impact of the center of mass of the multi-body system while moving, for example, putting some weight on the back of now, and then people see how the walk changes and might observe that and how it's programmed. Then information technology, programming by concerning different sensors and environment impacts. For example, if now wants to walk over there and there's an obstacle in the way, how he might observe that and how you can program that concerning different sensors. And electrical engineering, so most sentence or now says a lot, but in our case it's for example CPU is hot. So we want to demonstrate impacts of the program movements to temperature and computation. So what you might do better in the way of electrical engineering to improve that heat issue. And cybernetics, cybernetics is about control groups and collaboration and different research areas. We want to illustrate the connection between the different research areas and the application. And that, for example, if I want to do something with robots, I don't have to study mechanical engineering. I also can study, for example, social science. I get this later. So, working with now. Our approach, now is a very complex piece of technology. So, we don't want to have too much knowledge in the first sessions. They usually have about 4 to 5 hours in the lab. Additionally, there are some breaks, but then we have like 4 to 5 hours to teach them something. And as I said before, the dual cycle of learning, practical and theoretical phases passed in learning groups, so we switch. The general task is they should program now to perform a successful coaching. So first of all, they get the experience, same, they start playing with humanoids, so they get initiated and they observing stuff from the humanoids. After that, we make a reflection and ask them how does a human keeps his balance itself, how does a human walk, and what happens if you get pushed by a friend. So we want to tell them something about the center of mass and how it gets calculated. So hopefully they understand a little bit of the human sensor model, which keeps the balance. After that, they start to program with choreograph, and they first of all they will program the ball recognition, because first of all it needs to recognize the ball, and after that the path planning to walk there. So then we go on this knowledge which they already gained and made a reflection. They programmed that, and then we asked them what happens if now stands on one foot, because if you want to shoot a ball, at least you have to put up one foot. And what should you consider when performing a goal kick? Like this is again center of mass. It has to move, and you have to adjust the now robot to keep standing. They start to understand the interconnection between the different sensors and the motoric ability, how I can control the center of mass a little bit with the motors inside and the joints of now. So, and the other thing is that we break the problems down to the complex tasks to simple ones. They try, or they do the same, because in choreograph, you have those modules and you have to connect them together, and in order to do that you have to put the complex tasks into simple ones, so they learn that too. And then the intended action is that now we'll aim for the goal and perform the goal kick. So why use now in the teaching context? I think we have heard it a lot today already, but now as a humanoid, and on the one hand you have the general knowledge about your own body, and you can maybe use your own experience to solve problems with the now. The other hand, the scope is like a human body. The scope is nearly unlimited. We have everything to demonstrate, general topics with now. We have control loops by sensor fusion, image recognition, and moving in a 3D space. And you can demonstrate the complexity and variety of research areas if you're doing robotics. Programming now involves engineering, computer science, even social science over there, or we had here are sessions where you have human-robotic interaction and so on. And gender aspects are addressed as well, because the appearance of the body, the movement, the language usually attracts girls very much. We noticed that in the Roscoe, that if you make models of animals or human-like bodies, they are more attracted and interested in the subject. So, thank you for your attention, and if you have any questions, feel free to ask. Thank you.